Okay, so today we're going deep, really deep, into something that I think is absolutely fascinating.
Oh, yeah.
Nuclear reactions and radiation.
All right.
Yeah,
Yeah.
I know. I know. It sounds intimidating, right? Like something out of a sci-fi movie.
A little bit, yeah.
But trust me, it's actually way cooler because it's real. And it's happening all around us.
It is.
And it's used for a lot more than you might think. So lucky for us, we have an expert here to break it all down.
Yeah, happy to be here.
Before we dive in, though, you'll hear us talking about models.
Okay.
And when we say models, we're not talking about, fashion models or anything like that. We're talking about scientific models, which are basically like simplified representations of really complex stuff.
Okay.
So it's like, if you're trying to understand how an atom works, which is super complicated, you might use a model to visualize it.
Makes sense.
Right. Yeah. Okay, so let's talk about these nuclear reactions.
Right.
The standards mention something called alpha, beta, and gamma decay. What's going on there? That sounds kind of, ominous.
Right. Well, it's all about an atom trying to find balance.
Okay.
So picture the atom's nucleus, right? The center of the atom, like a busy city.
Okay.
Sometimes things get a little unstable.
Okay.
That's when radioactive decay comes in. And there's a few ways this can happen. Alpha decay, it's when the nucleus throws out an alpha particle, which is like a tiny package with 2 protons and 2 neutrons.
Oh,
Kind of like the city's sending out a delivery truck.
I like that. That's a good analogy.
Yeah. Then there's beta decay, where a speedy electron, also called a beta particle, zooms out. So that's more like sending a quick text message.
Okay, so those sound kind of similar, like sending stuff out.
They are, yeah.
What about gamma decay? That one sounds a little more intense. I don't know.
You're right. Gamma decay is different. Instead of sending out particles, the nucleus releases pure energy in the form of gamma rays.
Oh, wow.
So imagine a radio tower broadcasting a super powerful signal. That's gamma decay. And because these gamma rays are so high energy, they can be dangerous if you're exposed to them for too long.
Yeah, that makes sense.
So that's why there's a lot of, safety protocols around radioactive materials.
Right, definitely.
Yeah.
Okay, so we've got atoms breaking down in different ways, but the standards also mention fusion and fission.
Yeah.
Aren't those kind of the opposite of decay?
Exactly. Fusion is like, imagine the ultimate power couple. It's when 2 atomic nuclei, those tiny city centers we talked about, come together to form a larger nucleus.
Okay.
So you're basically combining these 2 cities into a bigger, more stable city.
So it's like they're merging.
Exactly. And it's powered by fusion.
Let's.
The sun.
Really?
It's constantly fusing hydrogen nuclei into helium, releasing a massive amount of energy, which keeps us warm and makes life possible on Earth.
Wow, so you're saying these tiny little atoms are basically powering the entire sun?
Pretty much, yeah.
That's mind-blowing.
It is.
Okay, so fusion is combining. What about fission?
Fission is like splitting that city into 2 smaller towns. We take a heavy nucleus and split it, releasing energy along the way.
Oh, okay.
This is what happens in nuclear power plants,
Right.
where we split uranium atoms to generate electricity.
Got it. So fusion is combining and fission is splitting.
Exactly.
All right, I think I'm starting to get this. Now, what about these half-life calculations? What's that all about?
So half-life is like a countdown clock for radioactive substances. It's the time it takes for half of the radioactive atoms in a sample to decay.
Okay.
So imagine you have a giant cookie,
All right, I like where this is going.
and you and your friends decide to eat half of it every hour.
Right.
After 1 hour, half is gone. After 2, only a quarter remains, and so on.
Right.
The time it takes to devour half that cookie, that's like a half-life.
I get it. So half-life is like a countdown clock, but wouldn't it be different for every element?
Absolutely. Each radioactive element has its own unique half-life.
Okay.
And that's important because it lets scientists do things like figure out the age of ancient artifacts.
Oh, wow, really?
Yeah, it's called radioactive dating, and it's like using the crumbs from that giant cookie to figure out when it was first baked.
So we can figure out how old things are just by looking at how much of a certain element is left.
Exactly. For example, we use carbon-14 to date things like fossils and ancient wood.
Oh, wow.
By measuring how much carbon-14 is left in a sample, we can estimate when that organism was alive.
That's incredible. It's like a time machine.
Kind of, yeah. But instead of traveling through space, we're traveling through time by looking at these tiny atoms.
That's so cool. Okay, so we've got these atoms breaking down. We've got fusion, we've got fission, we've got half-life. What about these other applications? I saw that nuclear reactions are also used in medicine and for generating power.
Absolutely. Nuclear medicine is vital in both diagnosis and treatment. It's like having superpowers for doctors.
How so?
Well, they use radioactive isotopes as tracers to see inside the body, like with X-rays and PET scans.
Oh, right.
These scans help doctors find and monitor diseases like cancer. And for treatment, they use radiation therapy, which is like using a super focused beam of energy to target and destroy cancer cells.
Oh, wow. So these reactions are literally saving lives.
They are, yeah. It's pretty amazing.
It really is. It's incredible how we can use these reactions for such different purposes. But hold on, if fusion is so powerful,
Yeah.
why aren't we using it everywhere? What's the catch?
That's the million-dollar question. While fusion is incredibly powerful and produces very little waste, it requires extremely high temperatures and pressures to get started.
Like, how high are we talking?
Think millions of degrees, like the center of the sun.
Ooh.
Yeah, scientists are working hard to figure out how to create those conditions here on Earth in a controlled way.
So it's a challenge.
A big one. But if they succeed, fusion could revolutionize energy production.
Right, the potential is huge. Well, I think we covered a lot today.
We did.
We learned about different types of nuclear reactions, from decay to fusion and fission, and how they're used in medicine, energy production, and even archaeology.
It's all about understanding these processes happening at the atomic level.
It's pretty mind-blowing when you think about it, right?
It is.
For everyone listening, I hope this deep dive has left you with a sense of wonder about the world of nuclear science. Who knows what mysteries are still waiting to be uncovered? So keep asking questions, keep exploring, and maybe you'll be the one to make the next big discovery.
Well, I hope so.
All right, that's it for today. Thanks for joining us,
Thanks for having me.
and we'll see you next time on The Deep Dive.
See ya.